Okay. Today I will be giving a presentation about using ImageJ alongside the plugin I've developed to analyze VCell simulations. And to start off, I'll be doing a high-level overview of everything that will be discussed in this presentation. So, uh, it will be experiments using microscopy can be recreated within VirtualCell. Any spatial simulation can be exported and opened in ImageJ using the plugin Simulation Results Viewer. And the entire toolset ImageJ has is available to simulations opened using said plugin. Um, so some terminology I want to go over for people that aren't fully familiar with ImageJ so that the rest of this presentation goes by smoothly. To start things off is ROI, or region of interest. Uh, that's just an area that's being focused upon within an image, and it essentially is the only region that is being measured to some capacity. So to show this visually, it would be as if only the yellow box is present within that previous image. Hyperstack slash virtual stack, that's basically just a multi-dimensional image. This can mean it has X, Y, Z spatial dimension time and multiple light wave channels, and it's just ImageJ's representation of such an image type. And then finally, ImageJ slash Fiji. They're the same exact tool. It's just that Fiji is batteries included version of ImageJ. So if I use the words interchangeably, they mean the same exact thing. Okay, so let's move on to the focal point of this presentation, which is bleaching a neuroblastoma cell. So as you can see here on the left, uh, we have a cell that has a bleached region of 10 by 10 microns. And then here's that same cell post-bleach. And in this experiment, we want to determine the diffusion coefficient of the bleached fluorescent. And there are plenty of methods to do so, but let's go ahead and use VCell simulations uh, for the sake of this presentation. So we have an experiment we conducted, and we want to recreate within VirtualCell. So that comparison between the two is straightforward. An extremely high-level overview of what that means is they should have similar geometry and physiology. The time step taken between each picture taken by the microscope should be the same exact for the simulation, and the bleached region should be similar in area and concentration. Uh, yeah. So we've created our simulation, and we got our results, and now we need to take said results and compare them to our experiment. Uh, this is where ImageJ steps in. So VirtualCell's strength is its simulation capabilities, but as its focus is upon creating simulations and returning results, there is no easy methods to take a simulation and do statistical analysis internal to the tool itself. However, if we create an image from our simulation results, then we won't have to use VirtualCell for creating regions of interest and performing statistical analysis. So by creating an image instance of the simulation results, this image can be modified just like one taken from the lab in ImageJ, and you can do anything you want with it. And with that being said, you can create a region of interest of only the bleached region and have easy analysis comparing the two regions of interest or the areas as depicted right here. So we understand how ImageJ is the optimal platform for this particular experiment. So let's go ahead and export our results to ImageJ. Okay, so within VirtualCell, there's the specific file format .n5, which is compatible with ImageJ. And so long as the specific plugin I've developed is used, the process is perfectly fine. And the process of exporting would be save the N5 export using VCell onto our servers. And then now with the ImageJ plugin I developed for VirtualCell, we can take said exports and ask for them from the server and then open them up with an ImageJ. With the additional perk that the exports have the geometry of each region essentially saved, or domain essentially saved. So you could do image segmentation uh, easily. But now that we've gone over how to use an ImageJ export, let's actually do it. And that's why I've been talking fast this time, is so that we have enough time for the demo. And hopefully it'll be fun. So, oh, that is my bad. Okay, please give me a minute. Okay, so the demo portion. And I'll be showcasing everything I've said so far. So to start things off, let's go ahead and open up the plugin I've been talking about that allows you to open up your simulation results. And if I'm able to annotate, yes, there we go. Right now, I'll be highlighting the different sections of the plugin, just so that you can explicitly see. So this top region is used for controlling the simulations, whether or not you want to open them or measure them. This center region is the list of all the different exports you've created already. Finally, this lower region is the area where you'll see details about said export. So the variables you've exported and the parameter values you've set. And then finally at the bottom is a simple filter that you can use to filter out all the exports you've done. So if I only want to see demo related exports, I just type it down there. Okay. And let me go ahead and remove all of that. Clear all drawings. Okay. So as you can see here, I've created several simulations, each with a different diffusion coefficient, trying to determine which one best accurately describes the lab experiment that I've conducted, that has been conducted. So right now, what we would want to do is simply open up one of these said simulation results, and then go ahead and determine the region of interest. That one's not as good. Let me do diffusion coefficient of 1. As you can see here, the region of interest that has been bleached, and create just a simple square over it to highlight the area, and then make it so that we only record data of that specific region, so that we can better determine the diffusion coefficient. I've already done that, and for the sake of time and brevity, I'm going to go ahead and just simply skip over that portion. So we've went ahead and created a region of interest. We've gone over the sort of different simulations I've exported. Now what we'd want to do is to simply take the lab results and then compare them to our simulation results. And we could do that fairly easily with the measurement script that's built within the plugin. So we want to highlight all of the different simulations we've already exported with the different diffusion coefficients, and then go ahead and click Run Measurement Script. And in doing so, we need the experimental image. So that's the image of the neuroblastoma cell. And then go ahead and open that up so that it can also be measured. We then go ahead and open up the regions of interest that have been saved preemptively that highlight only the bleached region, so that that's the only area of the cell that we focus upon. Next, we finally choose the measurement type we want for extracting data. So we can choose average, standard deviation, maximum, minimum intensity for, again, the region of interest of the bleached cell. We could do all of them, any combination of them, and the amount of measurement types can be added upon. If anyone has any comments of which ones they would want, uh, post them in the chat. And maybe in a future update it could be added. But for now, we just want average. And then finally, the format we want of the sort of data extracted is a wide CSV table, just because we'll be doing manual analysis and it'll be easier to do so. So, okay, we now would just want to go ahead and save all of that data and information into a CSV file. And let's go ahead and just call it demo. Save results. And now we'll open up all of the simulation images automatically, as you can see, create a region of interest for each image, go over each time slice and record the data for said image, and then save it to that CSV file, automatically close all of them. And now what you will have at the end is, let me go ahead and open it, all of the data regarding that particular region of interest. And the specific formatting of the CSV file is the first column is always the experimental image, and then all the others are the simulation results that you've conducted. And the titles of each column is as follows. It's the name of the image, um, the name of the region of interest, and then this particular variable that you've exported or channel, depending on how it's named. And that way you're able to determine what each column is representing in all of its data. And I've already created a CSV file that has all of this data already computed with statistical measurements. So I'm going to just go ahead and open that one because we don't need to do that manually. And this would be more of an end result of that previous export CSV file you've already saw. So to go over this quickly, I just computed the variance between the experimental image and each simulation to determine which one has the lowest variance um, and which one seems to most accurately describe what's occurring. So a quick overview of all these different final summations seems as if the diffusion coefficient of, oops, sorry, the diffusion coefficient of 1 seems to be the closest towards our experimental image. But if you go ahead and look at the graph I've also created, with the experimental image being the line that's blue with squares, it seems to fall in between a diffusion coefficient of 5 and 1. So in that regards, um, if we feel comfortable enough with a variance of 0.15, uh, we can go ahead and continue on with our experiment and draw conclusions potentially from it. But if we want something more accurate, we could instead do another experiment where the diffusion coefficient is equal to 3, and then measure it and figure out whether or not it more closely fits and resembles what's happening in the real world. And in that regards, that is the demo portion. So to go ahead and end things off, conclusion. So highlighting the points I made at the beginning of this presentation again, experiments using microscopy can be recreated in virtual cell. Any spatial simulation can be exported and opened in ImageJ using the plugin simulation results viewer. Comparison to microscopy imaging is simple using the ImageJ plugin. and the resulting measurements are stored in a CSV file where any further statistical analysis can be applied. Okay,